We've been talking about techniques for determining the parameters of a given functional form in the context of subjectively determining a prior density. And one method that is discussed in our textbook is what's called the technique of equivalent sample size, or it's also referred to as device of imaginary results. And in a previous video, we had looked at sort of a first introduction to Bayesian analysis and determining a posterior distribution. And we got this particular posterior, but only in the case that n equals 1. So that was just to give us an idea of what we mean by a posterior distribution. I think in the future we will come back and do this in a more general setting. So here we have a random sample, x1 until xn, from this normal distribution. And remember, theta is our unknown parameter, which we treat as random. And the sample mean x bar has that distribution there. We all should be familiar with that. And so remember that in this example, we felt that a normal prior density was appropriate. So that's a very important key, because clearly not all, and maybe perhaps few situations fit this case where a normal prior density is appropriate. Once we know that a distribution is normal or from a normal family, we've got to select the prior mean and the prior variance. And so here we're going to focus on the selection of the prior variance. And that's what this method helps us to do. So in this setup, the posterior mean is what we see here. And I do believe that the posterior distribution, the posterior distribution will be normal here. And so this is the posterior mean of the distribution. And so hopefully you notice that the form of that posterior mean is that it's a weighted average of x bar, right? It's a weighted average of x bar and mu. Now remember, we have to always be cognizant of the things that are known and the things that are unknown. So we're assuming that we know what the prior mean is. That's usually easier to determine. N changes, with our sample size. And of course, x bar is the particular realization from the sample. So here's the idea. This really is a weighted average of x bar and mu. So remember that mu is a subjectively determined mean. That's, based on probably someone's expertise in this particular area for this particular problem. And x bar, of course, is determined from the data. So the idea is that we need to choose an n, which they're going to refer to as n star. We need to choose an n so that we value the subjective guess at the prior mean just the same as we now value the x bar, which we got from the data. So it's kind of like we want a 50-50 gamble. And the question is, what n value, how much data would we need? And then we'll say, okay, now at that point, I value our prior mean about as much as I value the estimate of x bar. At that point, we would consider both of them to have roughly the same value. Then at that point, the right n, and we're wanting the smallest little n, but it's got to be, big enough. Then at some point, essentially what we would have here is a weighted mean where this is 1/2 and this is 1/2, right? Both of the weights, you can see where the check marks are, would be considered 1/2. And at that point, they're equal. And so you can kind of tell that sigma squared plays the same role as 1/n. And that's the key. That's the key thing. So if we choose an n, we call it n star, to where we value our subjective guess, the prior mean, the same as what we get from the realization from the data, then that little n will give us basically a way to determine an appropriate prior variance, which is what we wanted. And that's essentially what I've written out here. Okay, and then we can also consider CDF determination, which you can see on page 81. And as its name implies, we need to determine several fractile points. And then we can use those sort of as hinge points and then fit a smooth curve and get a cumulative distribution function. Then, of course, we could take its derivative and have a density function, a prior density.